What's up, AP Precalculus students? We are going to get into the homework where we're manipulating exponent functions. What we find is that certain transformations we think of when dealing with exponential functions actually can be written two different ways. Like a horizontal translation we find is this type of transformation as well. A um, vertical dilation is this type of translation. So let's get into it once I find the homework. Cool. First things first, and we didn't really have this in our notes, but we need to be comfortable with negative exponents and fractional exponents. We had this in unit 0, so this is kind of a reminder. What happens if we have exponents that are like negative a half, 2/3, 3/4? What do we do here? So a couple properties that we're going to be dealing with a lot are the following. First property is a power to a power. We will either write as a product or we'll take this product and we'll split up. Most of us are used to simplifying in this direction, but you'll see in today's class sometimes we will want to go in the other direction, which is new for you. Another exponent property is your product, x squared times x cubed, x is a sum. Again, sometimes we'll want to go this way, but sometimes we want to go that way. The reason why I bring this up is because we actually use this property when we're evaluating some fractional powers. For example, f to the negative 1/2, 2 times 4 to the negative 1/2. Talked about exponential functions, it's a multiplier, so that means a negative power would be a divider, or we flip things. We're not taking 4 to the 1/2, we'll take 1/4 to the 1/2, and that's just 2. We get our answer as 1. The half power is a square root. Okay, g to the 2/3. This is why we brought up the whole power to a power. Here we have like a product. We have 2 times 1/3. What I'm going to do is rewrite this, and we did this in unit 0 as a 1/3 squared. I'm going to do the root first because it's easy to do this in this order. I don't want to square 8 and then cube root it. I'd rather cube root 8 and then square it. So I get 2. 2 squared is 4. 3 times 4 is 12. So that's g of 2/3. Let's go h of 3/4. So 8 times 1/16 to the 3/4. Again, I don't want this 3/4 power. I don't have a calculator. We're going to go backwards here, where it's like we have a product. We'll write it as a power to a power for exponents. So I get 8 times 1/16 to the 1/4 cubed. 2, 4, 8, 16. We need to know that 2 to the 4th power is 16. So the 4th root of 16 is 2. 4th root of 1/16 is a half. Cubed, I get 1/8. 8 times 1/8 is 1. We need to be comfortable with fractional powers. J to the 3/2, 4 times 4/9 to the 3/2. Again, we will use this property, but backwards. We'll write like what we have as a product of two powers. We'll write 3/2 as a 1/2 cubed. Now, when we take the 1/2 power of 4/9, think about like a square power of a fraction. Like, what if it's 4/9 squared? Well, that would be 4/9 times 4/9, which will be like the top squared over the bottom squared. If you're taking powers of fractions, you can take the top and the bottom to that power. So I'm going to take 4 to the 1/2 and 9 to the 1/2, giving me this 4 stays here, but I get the square root of 4 is 2, the square root of 9 is 3. Also a reminder, when we are evaluating something with a square root, we don't need a plus or minus. When we are using a square root to solve an equation, we need a plus or minus. It's confusing for students that the square root of 9 is just 3. But if I asks you to solve x squared equals 9, you'd get x equals plus or minus 3. It's like, well, isn't that like the square root of 9 is plus or minus 3? No, it's that the original value, the x, could have been a positive or a negative x. It's the square root of x squared. That is the plus or minus x, or the absolute value of x. Anyways, you guys are probably just looking for the answers here. We got 4 times 8 27ths. So again, 2/3 cubed. 2 cubed over 3 cubed. I'm going to multiply the 4 over 1 by the 8 over the 27. There's nothing I can do to simplify. I get 32 27ths. Let's do some more with some negative powers. Probably the first thing I'm going to do, a negative power is like dividing. So we get the reciprocal to the positive 3/2 power. And then I'm going to, again, split this into a power to a power. I'm taking 1/4 to the 1/2 power, then cubed. So I get 2 times a half cubed. A half cubed is an 1/8. These are probably good ones to practice during class, because a lot of students with exponent rules, just like, they're like, oh yeah, I would have gotten that. I would have gotten that. And then you actually like do it yourself and you don't get it. I'm going to zoom in a little bit. G to the negative 4/3, that's 3 times 8 to the negative 4/3. Okay, first thing I'm going to do is write this as dividing by 8. Negative powers, opposite direction, kind of makes sense. Negative powers are dividing if we're talking about exponential functions being multipliers. Split this into a power to a power. The cubed root of 1/8 is a half. A half to the 4th is a 16th. So I get 3/16. Negative 3/2 for 1/16. First thing I'm going to do, a negative power is like dividing. Well, if I'm dividing 1/16, that's like multiplying by 16. Okay. I'm not going to take 16 and cube it. I'm going to take 16 and square root it first, and then cube it second. Square root of 16 is 4. I got to figure out what 4 cubed is. 4, 16, 64. 8 times 64. 48, 49, 50, 51, 512. Positive power is multiplying, negative power is dividing. If you're dividing by 4/9, you're multiplying by 9/4. So if I have 4, I put 4 times 4/9. 4 times 4/9 to the negative 1/2 would be equivalent to dividing by 4/9. It's the same as multiplying by 9/4. Flip with your negative powers is what a lot of people like memorize. The square root of 9 is 3. The square root of 4 is 2. I don't have any powers to powers. You could do 4 divided by 2 is 2 divided by 1. 2 times 3 is 6. You don't have to take the 4 and 3 and get 12 and divide it by 2. All right, cool. So that was a good review of powers. But now we get into exponential function manipulation and understanding equivalent transformations. First thing is first, and this helps us kind of in the future as well, is could you rewrite some exponential function? Could you write 36 to the x as 6 to the ax? Well, the key is to pay attention to that 6. It's like, okay, I want to rewrite 36 as like 6 to a different power. So watch what I'm going to do. I'm going to say 6 squared is 36. Then again, we go back to our powers. X squared cubed is x to the sixth. In this situation, I'm going to kind of go this way. First, kind of rewrite this as 6 squared. And then 6 squared to the x power, just like x squared to the third power, you can multiply the powers together. It's the rule that you could follow. Make sure you understand the rule. X squared times x squared times x squared. You get 6 to the 2x. So a is 2. A lot of you could just figure this out without doing that work, but we're going to show it anyways. Here, I'm paying attention to 2. I know 16 is 2 to the 4th. 2, 4, 8, 16. So I got 2 to the 4th to the x. I got 2 to the 4x. A is 4. Okay, now 4 squared is 16. But I want this 1 over 16. So I have to understand that a 4 to a negative 2 power, 4 to the negative 2 is the same as 1 over 4, or dividing by 4 twice, 1 over 4 squared, which is 1 over 16. It's almost like I pay attention to that 16 first, realize that I have to divide by 4 twice, understand we have a negative power, understand that a's got to be negative 2. Wait, I screwed up. Does this work out? I think I rewrote this the wrong way. I think it should be the other way around. Let me think about this. I need to rewrite this as 1/16 to a power. Okay, never mind. I got it. Sorry. You pay attention to the number first. I've been doing all of the other ones right, but this one tripped me up. You pay attention to 2. I'm going to pay attention to 1/16. And I got to think to myself, 1/16 to what power is 4? And this is like what's going to help us when we get into the future lessons when we're thinking about powers. Well, I know the square root of 16 is 4. Okay, cool. That means if I take the square root, but I kind of divide it, or if I take the negative power, I get 4 right here. Square root of 16 is 4. Flip it. The square root of 1/16 is 1/4. Flip it. I get positive 4. So that was tricky. This is 1/16 to the negative 1/2 x. A is negative 1/2. I was like thinking about this the wrong way. So like this is a similar one. 3. 3 to what power is 1 over 81? Well, 3, 9, 27, 81. 3 to the 4th power is 81. That means 3 to the negative 4th power will be like dividing by 3 to the 4th power, dividing by 3 4 times. Boom. 3 to the negative 4th is the same as 1 over 81. So 3 to the negative 4x is the same as 1 over 81x. So we get A is negative 4. Cool. Other way around. 6 to the 2x equals what number to the x? Well, this is, again, using your kind of properties to your advantage. What if I have the product here? We can go back and split this into a power or a power. Here's a product, 2 times x. Like 6 is 3 times 2, or 2 times 3, whatever. I could rewrite this as 6 squared to the x, which means we get 36 to the x. It's kind of like the previous problem, just in a different way. So we are manipulating functions. Now, what this equates to is honestly like horizontal translations with like different bases. But they're just questions where it's like, hey, are you comfortable writing equivalent forms of exponential functions? 27 to the 2/3 x, I would write as 27 to the 2/3 to the x. I would take the 2/3 and split that to a power. So it's like 27 to the 1/3 squared to the x. Cubed root of 27 is 3. 3 squared is 9. So I get 9 to the x. A is 9. Very similar here. I'd rewrite this as 16 to the negative 1/2 power to the x. Negative 1/2 power is like dividing instead of multiplying. So I'd have 1 over 16 to the positive 1/2. Square root of 16 is 4. I get 1/4 to the x. It's really just like the previous problems in the other way around, except for this one. 5 to the negative 2nd to the x is 1 over 25th to the x. Okay, cool. Now, we are going to have other stuff going on. We want to write the equivalent form as a times b to the x. So here's the key. I only want x, not anything else, times x, minus x, plus x. We got to get rid of that, so we just have a times b to the just x. So understand the prompt, and then you got to understand the properties. Now we've been using the power to a power property, so this first one's easy. I'd rewrite this as 16 times 4 squared to the x. I'm splitting up the product into a power, and I get 16 times 16 to the x. Some big mistakes made. The 16 can't be multiplied by the 4, so don't do it. Order of operations says you have to do the exponents first before you multiply. So you can't multiply this 16 and the 16. We're done here. That's a big mistake a lot of students make. Cool. Now let's go to these next two because we haven't looked at this property in a while. You are used to, when you're multiplying things, add the exponents. Well, what we're going to see is, and this is how I'll do it in class. If you have x to the a times x to the b, you have x to the a plus b. Sometimes it's advantageous to put it together. Sometimes it's advantageous to split it up. Here, I could write this as, and if this is like a negative b, this would be a minus b. I could write this 4 to the x minus 2 as 4 to the x times 4 to the negative 2nd. You are not used to doing this, taking this and going in the opposite direction. But here we go. Why do we do this? Because we just want x. Well, I see I'm going to have 4 to the x. But what's going to go on with this 32 and this 4 to the negative 2nd? Well, 4 to the negative 2nd is the same as 4 squared in the denominator, dividing by 4 twice. Now, we are multiplying these things together. You can't multiply this 4 by anything. We're going to leave this 4 to the x. But you can multiply the 32 and the 4 to the negative 2 together. A times b times c is the same as a times c times b. All good. The 32 and the 1/16 can be multiplied together to get 2. All of a sudden, we've just taken some function that has a horizontal translation, and we've turned it to a different function, like with a dilation, that's different than the original. In class, we kind of show this, the connection, and we'll do some of them later. And maybe I'll graph a couple. So here, you're not used to doing this, but you're expected to be able to understand that 4 to the x times 4 squared is 4 to the x plus 2. So I'm going backwards with my exponent rules. I then know 4 to the x is going to stay, but 4 squared can be multiplied by a half. I got a half times 16 times 4 to the x. I get 8 times 4 to the x. It's like we got this horizontal translation and this dilation too, just like a different type of dilation. It's pretty cool how it works out. Here, I want to write this. This is good. These are good ones. As just to the x power once. But it's like, what? I have x's twice. Well, let's see what happens. Let's go the other way, the normal way, the way we're used to, where I have, x to the a times x to the b is x to the a plus b. Well, let's go 3 to the x times 3 to the x. Can't do anything with that 8. I get 3 to the x plus x. All right, well, that's 3 to the 2x. Oh, 3 to the 2x can be written as 3 squared to the x. Now I just have x in one spot. 9 to the x times 8 is equivalent to 8 times 3 to the x times 3 to the x. Cool. Let's do another one. Lots of 2's. Can't multiply that 2 by anything, so don't. What I'm going to do is use my property where we can add the exponents. Cool. Realize that I have a certain amount of x's, 1 negative x. Realize that I could write this as 2 to the negative first to the x. Realize I can write 2 to the negative first as 1/2. This is what we want our answers to be. Man, did I make this homework? This is pretty. These are good questions. I don't know if I made these questions. Somebody else might have made these questions. These are good questions. Same thing here. I got 5 to the x plus x minus 1. Now, we got a lot of stuff going on here. What are we going to do here? 5 to the x plus x minus 1. 5 to the 2x minus 1. What do I do? Well, honestly, what I probably could have done is split this up right away. You could have written this as 5 to the x times 5 to the negative first and pull that out. You could have done it early. We could do it later. I'll do it now. I could write this kind of going backwards with my exponent rule as 5 to the 2x times 5 to the negative first. This is 1/5. 1/5 times 10 is 2. Okay, so I get 2 times 5 to the 2x. Well, I'm not done yet. I don't want 2x. I just want x. I'm going to write this as 5 squared to the x, product, power to a power. 2 times 25 to the x is equivalent to 10 times 5 to the x times 5 to the x minus 1. I mean, I just have to. It's like, it's cool. These equivalent situations. So hard to write. I guess I have to use parentheses. Okay, that's what I started with. I changed that to 2 times 25 to the x. Smack that on top of each other. Look at that. Cool. Yeah. All right, I'm going to do what I didn't do on the last one, which is before combining the 9 to the x's, I'm going to rewrite this so that it's times 9 to the first. 9 times 15 I'm going to do, though I don't want to. 135. Okay, so I get 135 times 9 to the x plus 1/2 x. Haha. What's 1 plus a half? 3 halves. 2 halves plus 1/2. I bet you so many of you are going to be like, oh, this is easy. And then you're going to start doing these problems and you're going to be like, yo, what do I do? So hopefully we're practicing. We're paying attention in class. We're getting this. 9 to the 3 halves. Don't want that. 9 to the 3 halves. I need to evaluate to the x. The square root of 9 is 3. 3 cubed is 27. Again, we rewrite this as 9 to the 1/2 cubed to the x. So I get 27. 135 times 27 to the x. $15 times 9 to the x times 9 to the parentheses 1/2 x plus 1. That's a lot easier, right? Is equivalent to 135 times 27 to the x. Hey. Ha ha! Ha ha! Aha! Sorry, having fun out there. What's going on here? Yikes. Well, watch this. This is x plus 3 divided by 2. 4 to the 1/2 to the x plus 3. That immediately becomes 2 to the x plus 3, which can be written as 2 to the x times 2 cubed, which can be written as 8 times 2 to the x. Yo, if you're struggling with these, like, you have to just practice them. They're good exponent rule problems. This is 27 to the 1/3 times 2x minus 1. What's the better way to explain this? X plus 3 over 2 can be written as 1/2 times x plus 3. That's probably what I would tell you to do if you're not understanding this. 2x minus 1 over 3. I'm going to rewrite this one extra step just to really show you what's going on. That's 27 to the 1/3 times 2x minus 1, which can be written as 27 to the 1/3 to the 2x minus 1, which is going to be 3 to the 2x minus 1. Cool. Keep going. That's 3 to the 2x times 3 to the negative first. I'm going backwards with my exponent rules, which is 3 squared to the x times 1/3, which is 1/3 times 9 to the x. That's great. That's just great. That's just great problems right there. 27 to the parentheses 2x minus 1 over 3. 1/3 9 to the x. That's just great. It's cool. All right. What vertical dilation is equivalent to a horizontal translation of left 2 for f of x? Well, first of all, we got to understand a horizontal translation. Left is when we kind of manipulate the inside of the function, but we're like order of operations. We got to start plugging in -2 to zero out the function. +2 shifts us less 2. Most of us just are cool with that. So first thing I do is like say, okay, here's my horizontal translation. Left 2, I get 3 to the x plus 2. But what I realize is that this horizontal translation using exponent rules is equivalent to a vertical dilation of 9. 9 times f of x is the same as f of x plus 2. This is like what we showed in class a lot. These are kind of fun ones. 3 to the x plus 4 is a shift of 3 to the x. Left 4 is what a lot of us think. Okay, so I move that point 0, 1 over to -4, 1. But what we realize is that it's the same as a vertical dilation of 9 plus 2. What am I doing? Oh, there we go. Right on top. It's the same as a vertical dilation of 9. Now, how can I show a vertical dilation of 9? Well, let's look at this point, 0, 1. Sure, you move it to the left 4 or left 2, and you got -2, 1. But take this point 0, 1, multiply the y coordinate by 9, and all of a sudden you get 0, 9. So there you go. Like, it's cool how those exponential functions work. What vertical dilation you'd be like? Vertical dilation by a factor of 9 is probably what you'd say. What vertical dilation is equivalent to a horizontal translation of right 3? Okay, so right 3 is going to be f of x minus 3. So I'm going to start with f of x minus 3, which is 2 to the x minus 3. But use some exponent rules. I get 2 to the x times 2 to the negative third, dividing by 2 3 times, 1 over 2 cubed, 1/8. We get that the horizontal translation right 3 is equivalent to a vertical dilation of 1/8 for 2 to the x. So there's that vertical dilation, factor of 1/8. And I could show you with Desmos, like you could take your 0.01, because the initial value's got to be 1 times 2 times 2 times 2. If I plug in 0, I get 1. I could shift that to the right 3, okay? Or I could take that point and multiply it by 1/8 and bring it down, and you'd get the same graph. It's cool. One more time, vertical dilation, horizontal translation, left 1. So left 1 is going to be opposite adding 1. So I get 4 to the x plus 1, which becomes 4 to the x times 4 to the first, which is equivalent to a vertical dilation of 4. For this function. Okay, what horizontal translation is equivalent to a vertical dilation of a factor of 1/16? Okay, so now we're going to go in the other direction. So the first thing I'm going to do is like, okay, vertical dilation of a 1/16 is when I multiply my function by 1/16. So I get 1/16 times 2 to the x. But what I want to realize is that this is equivalent to some sort of horizontal translation. This is when I kind of took values and made it a specific thing to a power. So I need to somehow make this 1/16 a 2 to a power. Well, let's see. 2, 4, 8, 16. And this is the one I screwed up with. All right. 2, 4, 8, 16 is 4. 2 to the negative fourth is the same as 1 over 16. Okay, you got to figure that out first. And these are going to be tricky for you, I bet. Using an exponent rule, you can rewrite this as 2 to the x minus 4, which means this is equivalent to f of x minus 4, which is a horizontal shift right 4. I'll show you for this one. Start with 2 to the x. Okay. Start with 2 to the x. It's got the 0.01. Let's do a vertical dilation of 1/16, which means I'm going to take this and I'm going to take all the y coordinates and they're going to shift down because I'm going to multiply them. So all of a sudden I got this 1/16 point. Boom. I could look at the point 2, 3, 8. You get my drift. There's 3, 8. Times the 16th becomes 3.5. Boom. But look, you could also shift over 1, 2, 3, 4 to get this 0.41. You could shift this 0.24 over 4 to get 6.4. You can see 2 to the x minus 4 is equivalent to 1/16 to the x. Cool stuff, but tricky stuff. Okay, we got some more. Vertical dilation by a factor of 27. So a vertical dilation of a factor of 27 is multiplying 27 by the function. So I got 27 times 9 to the x. Well, again, this is tricky. 9 to some number is 27. Okay, that's what they're trying to say. It's like, what is the horizontal translation? Well, like 9 squared is 81. I don't get 27. this is where I got to start thinking, and this is a little tricky. And in the future, we can use like some techniques to help us figure this out. The square root of 9 is 3. I know 3 cubed is 27. Oh, I got to figure out that 27 is 9 to the 3 halves. How are you going to figure that out? You just got to kind of work with what you know, which means you get 9 to the x plus 3 halves, which means a vertical dilation of 27 is equivalent to a horizontal translation left 3 halves. This is equivalent to this if f of x is 9 to the x. It's all about what you're starting with. Okay, so here's another one. We want to vertically dilate by a factor of 1/64th, not 16th. Okay. 4, 16, 64. 4 cubed is 64. 4 to the negative third is 1/64th. So 1/64th f of x is the same as 4 to the negative third times 4 to the x, which is the same as 4 to the x minus 3. Use your product properties, multiplying, add, which means a vertical dilation of 1/64th for 4 to the x is equivalent to a horizontal translation right 3. If you don't want to put this, you don't have to. It's just kind of like showing you that you get the same thing. There's like the translation form. All right, then we switch over and we find E. E shows up a lot in mathematics when dealing with infinities. We're not going to get into it much, why it shows up, because we're not going to do that many compounding interest things, which is the easy way to explain why it shows up. We just need to be comfortable with like it being a number similar to pi. It can be manipulated as a base of an exponential function, just like all the others. So I'm starting with f is 3e to the x. What is the y-intercept of f? So that's when I plug in 0 for x, so that's 3e to the 0. Okay, I got an initial value by 3. It's the same thing what we're dealing with exponential functions. Your initial times your multiplier over and over and over and over. So 3 times e times e times e. Why does the graph of f have no x-intercepts? You could talk about the end behavior. This is a situation where you're multiplying by something bigger than 1 every single time. Your limit approaches 0 to the left. It approaches infinity to the right. It never crosses 0 in between. That's probably not the best explanation, is looking at the end behavior, because end behavior doesn't explain what goes on in between. So I don't love this. 3 times e to the x is always positive, is probably what I'm going to just say. Like, a number to any power is always positive. It approaches 0, but it never equals 0. Write an explicit formula for g of x. I think they just want you to figure out that it's x minus 4 of f. So f of x minus 4 is 3 times e to the x minus 4. That's g of x. So if I asked what is g of 3.5, it's equivalent to 3 times e to the 3.5 minus 4. I'm not going to split this up. I will combine my numbers to be e to the negative a half, which is the same as square rooting e in the denominator, or 1/2ing e in the denominator, half power of e in the denominator. If g is written as c times e to the x, what is c? Okay, so if I have g of x, which is 3e to the x minus 4, I can write that so that I just have an x as 3e to the x times e to the negative 4th, which I would say, and now this is tricky, like 3 over e to the 4th is c. It's not a number, and that's okay. Like, this will happen. We just use exponent properties to bring it down. If I go left 1, That's equivalent to a vertical dilation of E. If I have a vertical dilation of 1 over E cubed, that's equivalent to a horizontal translation right 3. All right, this is like intense. There's a lot of good stuff here. And like, I know that I'm doing it and it's like I've done it before. So it's kind of like I know what to do. I can see how a lot of you are going to have struggles with this. The first time we start doing these exponent rules in different order, it's going to be complicated. So we got to practice. And if you just copy down this homework, you're not ready. You don't know what you're doing. Go back, make sure you do problems. Do problems. Understand your exponent rules. And that's the only way through things. And that's going to help you in the future moving forward in this unit. It's a big unit. We got 6 lessons in it. But it's a good unit. It's shaping up to be a really nice unit in terms of the way I think we're teaching it to you guys. So good luck out there.